All right. Okay, so let's get started here. I was asked to say a few more words about the proof that I just finished up with last time. So let me say a little bit more about this. So this is the so-called witnessing lemma, because for S12. By the way, can people in the back of the room see the handwriting well enough? Everyone's young with good eyes and that kind of stuff. Can the camera see the writing okay? Sure. Okay. So, so the idea is we have a so-called sequent. So a sequent we typically write as gamma arrows delta or some other capital Greek letters. This is some special sequent arrow. And what this means is gamma is a set of formulas and delta is a set of formulas. And here we're assuming they're all sharply strict sigma v1 formulas. So in particular, they all have the form, the outermost quantifier, if it's present, and it could be missing, but I'm writing it as if they're all present. Each formula has outermost quantifier exists x1 less than or equal to t1 through exists xk less than or equal to tk, and likewise for the things in delta. And then the inner part has a single sharply bounded quantifier, and it's polynomial time computable to check whether the property holds inside there. And the witnessing lemma says that the function that takes x1 to xk, which satisfy the property that they make the gammas true. Okay, so we take x1 through xk that satisfy the hypotheses here. It satisfies all of them. The ands on the commas on the left side of the sequent arrow mean the same as and. That this produces some value y. It's a polynomial time procedure. And this y will witness one of these formulas delta on the right-hand side. Okay, right-hand side. So this is the basic witness lemma. Says that you take witnesses that show that these things on the left-hand side are true, and they produce a witness for at least one thing on the right-hand side. And the property that's preserved is that this is polynomial time computable, provably in S12. The last line of the proof has the form exists y less than or equal to s, a of yc. And it's a sequent. The last line has one formula on the right-hand side and 0 formulas on the left-hand side. And so then the witnessing lemma applied to the last line of the proof says, given witnesses for everything on the left-hand side. Oh, I should have, sorry, let's correct this. Should have said we also get c as an input to the polynomial time function. Given c and giving witnesses for these 0 many things over here, we can produce in polynomial time a witness for the y here. So it's just a polynomial time function of y of c is giving you y. So that's the import of the witnessing lemma. Okay. Marco had a question.
Is it provable in S12? Like, can you prove the witnessing lemma in S12?
Okay, so again, we're dealing with we're back to the issue. We're dealing with a particular proof. We get a particular proof with only sharply strict sigma v1 formulas. For each line in the proof, S12 proves this statement. Okay, that's not the same thing as saying that S12 proves that given an arbitrary proof, there's no. That doesn't work, because in worst case, the cut elimination process in principle could cause super exponential growth rate in the size of proofs just to get rid of the sharply strict, just to get to only sharply strict formulas. And even then, the difference would be the following. Suppose you have a computer program that consists of 4 loops that all go from I equals 1 to n, so it's clearly time n to the k, but k is the number of lines or the number 4 loops in the program. You can't take a computer program with 4 loops and get a uniform polynomial evaluation of those things, because different programs have different number of nested for loops. Instead, any particular program has time n to the k for some k. It's not the same thing as saying take a computer program and produce its output. It's a harder thing, right? That's not polynomial time. We're saying it's for particular proofs. We have polynomial time algorithms. Other questions? Things I should discuss? The details of the witnessing lemma get pretty touchy. I'd rather not go into them. Don't have slides for them, and I don't think it'd be worthwhile going through it. But just as, OK, the comment here is, thus the main theorem follows immediately as a corollary. This is just the comment here I made at the bottom of the board here about the last line of the proof. Of course, this builds on considerable machinery. The cut elimination theorem is a fairly sophisticated theorem. I guess I could ask, how many people have seen the cut elimination theorem? Wow, good. That's pretty good. A third of you raise your hand. OK. 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 The crucial thing about the cut elimination theorem, let's just say a word about it, is our axioms. So we're proving a sigma b1 property. Our axioms, they're not sigma b1 formulas per se, but the induction axioms involve only induction on sigma b1 formulas. And we can exploit that fact using a special induction rule in the setting of the sequent calculus to say that therefore we can, because we're only using induction on sigma b1 properties and we're proving a sigma b1 property, we can restrict our attention to proofs which contain only sigma b1 properties as formulas in the sequence. So that's a fairly sophisticated theorem that says you don't need to go into more complicated formulas to prove things about sigma b1 properties. Okay. Okay. All right, so let's move on then. So first I want to mention that I proved this for I equals 1. I'm trying to keep life as simple as possible. I don't want to talk about it, but just mention that the same thing works for higher values of I, but now we have to go up to the higher in the hierarchy. Remember, SI2 was the theory with induction on sigma bi properties, which is P induction on sigma bi properties, which is induction on properties at the ith level of the polynomial time hierarchy. It can compute every function. It can provably, it can sigma bi define, not sigma b1 define, sigma bi define every polynomial time function which uses an oracle from the I minus first level of the polynomial time hierarchy. So you just sort of relativize everything to sigma bi minus 1 or sigma pi minus 1, and the same stuff works. Likewise, the main theorem still works. The functions which are sigma bi defined by Si2 are precisely the polynomial time functions relative to the I minus first level of the polynomial time hierarchy. Okay. And the proof idea, proof constructions are very similar, but since it's a first pass on learning bounded arithmetic for most of you, I want to stick with the I equals 1 case as much as I can. Okay. Okay. What's next? Oh, I just wanted to mention, this is not, I'm not going to prove this here, but let me just mention the general idea for how does one prove. Remember, I had this list of inclusions on the theories. So I already discussed that Ti2 contains Si2. So let me mention this other result that S22 is for all sigma b2 conservative over T12. Let's just do it. In general, this symbol means that Si plus 1, 2 is for all sigma b I plus 1 conservative over Ti2. That's what that funny curly symbol means. And what this means is that if phi is a formula, it's a form for all x psi with psi and sigma b I plus 1. And if Si plus 1, 2 proves phi, then Ti2 proves phi. So Si plus 1, 2, although it appears to be a stronger theory, oh, the other thing is, and, let's say that, and Si plus 1, 2 contains, Si plus 1, 2, yeah, contains Ti2. So these are the two parts of being conservative, 1 and 2. Si plus 1, 2 is a stronger theory, possibly stronger, at least no weaker. It contains the other theory. And furthermore, that for any formula in this special form of for all sigma bi plus 1, if it's provable in the stronger theory, Si plus 1, 2, then it's provable in the weaker theory, Ti2. So the stronger theory doesn't contain any new facts that are low complexity. That's what I mean by this conservativity result. Okay. So let's see. There's probably a question or two on this definition here. Is this sort of confusing the first time you see it? another way to think about this curly less than sign is it's saying that, so let me write it out.
So when you write subset, it means strictly that every formula in the closure of S12 is also in T12.
Right, so subset means, here I put the equal sign again because I cut and pasted. So subset means, yes, that the theory S12, every theorem of that theory is a theorem of T12. Right. Okay.
And then
so
this curly thing is,
the curly thing means,
restricted to sigma 1, 2. Is that what you meant?
So the curly thing means a subset, plus, in addition, nothing new of this complexity class. So I've got low complexity formulas, the for all sigma B2 formulas. Nothing new gets added in when you go to SI plus 1, 2, but other more complex formulas may be in the theory. Yeah. So it basically means subset, but equal on the class I marked there. Right. Okay. Okay. In particular, so this means, for instance, that SI plus 1, 2 and TI2 have the same sigma bi plus 1 formulas, sigma 1 definable functions. And also the same sigma bi definable functions. Because a sigma bi plus 1 definable function is defined in terms of a for all sigma bi plus 1 formula being provable. And they have the same provable for all sigma bi 1 formulas. Okay. So these theories are very similar in strength, certainly in terms of what functions they define. Okay. So I just want to say the proof, I really don't want to do this proof at all, but just to say to prove this, basically what you show is that the witnessing lemma, which I described on the previous pages, where I said that SI, well, I guess where the analog for the higher values of I would be, where I said SI plus 1 can prove something, SI plus 1, 2 can prove something, it also follows that TI2 can prove the same thing. So it takes a little bit of work, but you can show that actually the witnessing lemma can be carried over the base theory using TI2 instead of SI plus 1, 2. And then this follows. Okay. So it helps show, again, the power of the witnessing lemma. It really shows us exactly what can be done in these theories.
Why didn't this curly, why didn't you just do a subset equal subscript?
Subset equals subscript. Well, because this is a traditional logic notation.
Oh, really?
Okay. So, you go back and read old logic books, from model theory, Chang and Kiesler is where I first saw it, and this is the notation they use. Okay. So, yeah. It's a good enough, I guess, yeah. Okay, what's next? Okay, so I guess that the other thing, okay, there's two comments on this slide. First of all, let's do the second comment first, is although I just said SI plus 1, 2 is conservative over TI2, in fact, if they're equal, so that means they're rather similar in strength, but if they're actually equal, then the polynomial hierarchy collapses, provably in these theories of arithmetic. So it's unlikely they're equal, but who knows, right? Maybe the polynomial hierarchy does collapse. So, but the general conjecture would be, and we have some experts in the room on this too, would be that the polynomial hierarchy is distinct. All the levels are different, and that would mean these theories are distinct.
And that's related to non-uniform sigma pi plus 1, not.
Oh, okay, so the hierarchy collapses, so here I was maybe saying more than I should have. The hierarchy collapses to non-uniform sigma pi plus 1 with polynomial mounted device, or to uniform Boolean combinations of sigma pi plus 2, and thus to sigma pi plus 3 equals pi bi plus 3, right? Okay. Yeah, this might be a little better than, Ben, do you remember this? Maybe a little better than Karp-Lipton gives you right away, but you can get it from the provability. These facts are also provable in the theories, not just that it collapses, but the theories can prove it. They prove the collapses to these levels. Does Karp-Lipton give you down to this? Maybe it only gives you to sigma bi plus 3. I'm not sure now. Okay. Okay. So it's unlikely. So probably everything's distinct. On the other hand, we know no reason why maybe SI2 might be equal to TI2. right? Instead of going from the t up to the next s, going from s up to the next t, maybe they're equal and we don't know any strange things that follows from that. Yubi?
If you separate these theories, is there any evidence that the polynomial hierarchy doesn't
If we could separate these theories, that would be evidence, that would show that these theories don't prove the hierarchy collapses. So if you could separate these theories, you could show that they don't prove the hierarchy collapse. And that would be actually really excellent indication, especially for starting at T22 and S32 and going up. The natural proof methods only apply to, I'll say a little bit more about this later on just in passing, to T12 and S22, natural proof methods apply to those. They don't apply when you go any higher up. So it'd be a breakthrough to show, for instance, that S32 can't prove the polynomial time hierarchy collapses or something like that. That would be a big theorem. Okay. Of course, we'd rather prove the polynomial time hierarchy doesn't collapse, or maybe even that p is not equal to np, but we would start with it doesn't provably collapse. We'd be very, very happy right there. The other comment is, if you go, remember I talked about provably total functions. And there, the property that you had to have for your function was supposed to be a polynomial time property. A sub f, I called it, was supposed to be a polynomial time thing. And that corresponds to sigma b1 definability. These other theories outside of S12, we've only been talking about sigma b2 and up definability. And so we want to come back and see what can we do about sigma b1 definability in these theories, because that corresponds better to provably total than what I defined earlier. And there's the end of my first hour of talk. Okay, good. So I'm pretty much on schedule, not too bad. I can adjust later on, not to worry. So part 2 of the first set of slides, okay. Okay. So let me shift gears away from bounded arithmetic for just a minute, and we'll come right back though. So there's this computational complexity class known as polynomial local search, PLS. It was defined by Johnson, Papadimitriou, and Yannikakis in '88. So there's a lot on the board. It's not confusing once you figure out what it is on the screen. So we've got a polynomial local search problem. We're thinking about doing a local search to find a local minimum for some we've got a domain of so-called feasible points. Each feasible point has a solution, has a cost associated with it, and we've got a neighborhood function given by function n. And the idea is to find a local cost point, a local cost feasible point. So f, the predicate f, picks out the feasible points. Our input is x. That's the parameter everywhere. So the desired output is a solution s. And first of all, we've got a polynomial bound. Whenever fx, for every possible solution s, s is less than some polynomial bound on x. Okay, so our solutions don't get too big. We have a known initial point. I of x is initial. This is some unknown. There's at least one place is feasible. So this tells us this. And then now here's the sort of, well, actually let's do the third one here, the fourth, whatever it is, the last one. If s is a feasible solution, then n of xs gives us another feasible solution. So we've got an s, and we can take n of it, and we get another value that's also feasible, so f holds of it. And then finally, either this next function gives us the same thing back, or it gives us something of lower cost. So the cost, either the cost of n of xs is less than the cost of s, or n of xs just stops. And all of these things are polynomial time computable. So all of these things are efficiently, quickly computable. The original definition of PLS actually used n returned a finite set of neighborhood solutions, but you can equivalently, at least from the complexity point of view, talk about just getting a single solution. So that's what we do for simplicity. And it's guaranteed that if you have a PLS problem, that there's always a solution. Because the costs are assumed, I haven't said this here, but the costs are non-negative integers. So we have minimization on non-negative integers, and so there has to be a minimum cost solution. Thus, there has to be a locally minimum cost solution. So thus, there's at least a solution, right? There may be lots of solutions, but one way to find it would be to start with the initial, one way to find a solution would be to start with the initial thing and hit it repeatedly with the n function, the next function, until you reached a loop at the end, right? That might be an exponentially long procedure to do that. So then the question would be, maybe there's some way to shortcut that process and go straight to a feasible solution. Think of, for instance, in linear programming, right? Danzig's algorithm had exponentially many things could happen, but nowadays we know there's polynomial time methods to jump through the interior, as it were, and find solutions by some other method. Okay. So this is PLS. I is the initial point. So it's just some place that's feasible. Just to say there's at least one place that's feasible, and furthermore, we know where it is, so we have evidence that there's something that's feasible. Right. Okay. So that's just to make sure that we really have evidence. The point here is actually the real goal of the polynomial time local solution of the PLS problem would either be to find a local minimum, or to point out that I of x fails to be feasible, or to find a place where the next function or fails to satisfy one of these two properties, right? Would be another way to talk about it. Okay. Okay. Other questions on this?
What's the third one? Can you repeat?
Number 3 or number 2?
3.
3. Okay. So if S is a feasible solution, then the neighborhood of S is a feasible solution. This is, in some sense, a bit of a historical artifact here, although it's useful for other applications, so it's always left in. The point is just there's some solutions that aren't valid at all, and then there's some solutions that are potential solutions but maybe have too high a cost, and we're looking for a minimum cost. Okay. Okay. So on linear programming, maybe you have some solution on the polytope that's not optimal. It's still a solution. You could still use it, but it's not something that's the best solution, right? Okay. And these are actually a special case of what are known as TFNP problems, and I'll probably talk about them later on. So more generally, any sigma b1 definable function of a theory, and sigma b1 definable is particularly important here, is, well, special kinds of, maybe that's not quite true, but I'll say that, is a kind of a TFNP problem. The TFNP problems are so-called total functions NP is what this stands for. And it's a set of polynomial time, it's a TFNP problem is specified by a relation R of x, y, such that R is polynomial time as a predicate of x and y. And R is polynomially bounded. Think of x as being like the input to the PLS problem and y as being like the solution S. There's a polynomial bound on y, and R is total. For every x, there is a y, such that R of x, y. So this is a general way of specifying functions, and, well, actually multi-functions, because there may be multiple values of y. But we know there's at least one y, and we know that once we've found one, we can recognize that it's a y. Okay. So the PLS problem is like that because, well, because you can just see that this satisfies the properties. Sigma b1 definable functions are like that because, well, if you did this contraction of the yz like I did earlier, you can in polynomial time recognize you have the answer. And so both of these things feed into this. There's a lot of work on TFNP, which I don't want to get into right now. But let me instead go back to bounded arithmetic and talk about PLS in the theory T12. So where we're going is the sigma b1 definable functions of T12. This is that's sort of our next topic for the talk. And the first comment is then that any PLS problem can be done total in T12. So the polynomial local search problem, we'll say that a PLS problem is formalized. I said S12 at the top, but I could have also said T12. If the feasible set property F, the initial point function I, the neighborhood function N, and the cost function C are all polynomial time functions, or at least sigma b1 defined functions of the theory. And then the theorem, the first theorem, the easy direction, is that T12 can prove any formalized PLS problem is total. And the basic idea is you just say we're going to use T12 has induction on sigma B1 formulas. Induction is a form of minimization. I'm going to wave my hands here just a little bit, but it's true enough. And so T12 can say there's a minimum cost value C sub 0, which satisfies the property that there's some solution S which is feasible, and or I should say some feasible point S, which has cost C0. So we look for we can prove the existence of a minimum cost over all feasible values S. So once you prove the existence of a minimal cost, well, that means there's at least one S that goes with it. Any such S has to be a local minimum because it's a global minimum for the cost. Okay. So this gives a way in T12 to prove this. You have to prove the minimization as well, but that follows pretty easily from induction. Okay. Converse, yes. Well, I'll state the converse in just a moment. Yes. Converse is true too. Yeah, or a converse. You know. I have to state it real precisely though.
But didn't you say before that there is a theorem that says that T12 is, I forgot it, T12 is the same as polynomial time computable function. The provably total functions of T12 are?
Oh, okay, so for T12 we have that the sigma B2 definable in T12 is the same as polynomial time relative to sigma B1. As a, say, or in S22. So we have this conservativity result of S22 over T12. And so the sigma B2 definable functions of T12 are the same as polynomial time in which is the same as polynomial time in NP, right, in the more familiar complexity language. Okay. But now we're talking about sigma B1 definable functions. It's a different thing.
I thought that before you said sigma B1, you found that T12 is the same.
As?
Because sigma B1 definable is the same as, in this context, the same as provably total.
Oh, yeah, so, okay, so this is back to the notion of provably total. But provably total was there as a motivational thing. I haven't actually proved any theorems about it. But I want to say sigma B1 definable is the right analog of provably total, and that's what we really want to be interested in the end. You know.
What is the, well, you'll show us in the next slide, but what is the difference between this and, PLS is a subset of polynomial computable functions.
PLS, no. We don't know whether PLS can be done by polynomial time computable functions, right? This open question of whether there's a polynomial time method to solve PLS problems. By which I mean it's open whether there's a polynomial time method to find a local minimum, right? Open question. In some cases, like Danzig's algorithm, it works out. Other cases, it's open. Okay. Okay. So here's the exact statement then here. If you have a sigma B1 formula A, and T12 proves for all x there exists a y, A of xy, okay, then there's a PLS problem R such that T12 proves that if you have a solution y to the PLS problem, you can extract immediately from y a value such that A holds. So extract immediately just means the project out with the Gödel beta function, for instance, or use a polynomial time method to extract it. So the point is, if you can find a PLS problem such that from solutions of it you can get a solution you can find a y such that A of xy holds. Okay. Another way to say this is the sigma B1 definable multifunctions of T12 are precisely the projections of PLS problems. So projections, I mean project out one of the coordinates or one of the components of a sequence. So this gives a very precise definition, the precise characterization of the provably total functions of PLS. Okay. And, so where does this projection thing come from? Maybe I should say more about that. It's, again, from what I wrote earlier. Suppose T12 proves for all x exists y less than or equal to t. And now here I've got a sigma b1 property, because it's a sigma b1 definable thing. So this is going to be an exists z less than or equal to s phi of x, y, z. Right? This is what we mean. So phi is, this is delta b0, and hence polynomial time. Okay, well then you can think about the function x that goes to the pair yz. This actually turns out to be solvable by a PLS problem. Okay, because getting both y and z you can solve with a PLS problem. Getting just y, so x maps to just y, is solvable by a projection of a PLS problem. Because we can get yz by solving a PLS problem, and then we can project out to get y. Okay. Okay. So, all right. The proof idea, once again, I'm not going to try to do this. It's another witnessing proof, but it's then a little even harder than the last one. Basically, you just, again, do sort of witnessing stuff. If you've got witnesses for the things on the left-hand side of a sequent, and you have a solution to an appropriate PLS problem, then you get a witness to something on the right-hand side of the sequent. This is the witnessing lemma for this as well. And the proof idea here, again, is you take a free cut free proof, and you go through it as if it's a program. But now the inductions are regular inductions. So if you unwound them in the usual sense, it'd be like an exponentially long iteration. But instead you use the fact that the cost function can take on, it has a range that's exponentially big. So you can use the cost function to sort of count your time through the loops. And so rather than going through the loops, you just have a cost function that measures how far you are through the loop. And that's about all I'm going to say about the proof, because it's very picky details, I guess. Okay. All right. Okay. Questions on this?
So it might be helpful to, do you have like a PLS problem that you can describe?
Do you have a PLS problem that I can describe? Well, I said,
in other words, you say, this is what we want. I mean,
right.
At the end of the day, it's an optimization problem. So
Mm-hmm.
typically, you think of a set of constraints and objective function. That's
Yeah.
a typical definition. And here I'm going to define the functions n, I, c, and so on. And
Right.
this way.
So, I mean, okay, so he's asking for an example for a PLS problem. I don't have a readily easy one to give you. Danzig's algorithm maybe is the most obvious one, where you can see that you're minimizing the cost of your solution that way. Is there an easy, I guess I don't have an easy one to give you right off, okay? Yeah.
So another way to think about this is, you want to find a global minima, say for LP, for example, but
Mm-hmm.
you can then define a corresponding PLS problem, because many algorithms perhaps do neighborhood search
Right.
in their attempt to find a global minimum.
So the question is about converting a global minimum search into a local minimum search. So, I mean, there's a lot of heuristics. A lot of times people do things like, you're looking for a global minimum, you may do a local search of some type to look for a local minimum, and then you restart and try again and look for another local minimum, and then you hope that one of those things is a really good local minimum that, although it may not be the global minimum when you're done, at least it's a good stand-in for the global minimum, right? So, yeah, so you could think of each iteration of this process as a local minimum search kind of thing. But that doesn't give you a solution to the global minimum. That's a different thing, right? Okay. Pause. What does pause mean? It means I might have stopped here on an hour break, but I didn't. Yeah, but it's a question.
Is there any connection between the open question that you listed?
Oh, yeah, I skipped that one.
Functions and general purpose search to decision reductions, or is that?
Oh, let me. This good question is, what about this open question I skipped earlier here? Okay, right? But Marco picked up on is here I was talking. See, here we're talking about multi-valued functions. There may be more than one y that's a solution. And that's a difference between T12 and S12. For S12, if we could prove there exists a y, we could actually prove there exists a unique y. And the way that would work is follows. You prove there exists a y, then you prove there's a polynomial time Turing machine that produces a y, and then you could say that polynomial time Turing machine produces a unique y. And so you can sort of uniquify your y by getting it via a particular polynomial time process. We don't know if that's possible with PLS and T12. We might, even if T12 can prove the existence of a y, we may not have any way to uniquify that y, to strengthen the condition to make the y unique. So we just don't know that. That's an open question. Does that say about something search to decision? I don't have any idea. I sort of doubt it. Marco's shaking his head, so I'll say no. Okay.
It's about canonization, not search.
Oh, canonization. Well, maybe. Okay. But the point, I think if you could get it yes, it would have to somehow exploit the existence of the T12 proof, or prove something pretty amazing like NP equals NP intersect co-NP or something like that, you know. Okay. So, okay.
So my understanding is that for S1, let's talk about S12. So S12, the sigma 1 definable functions are precisely the polynomial time functions, and then you want to know, and this gives you the corresponding characterization for T12.
Yes.
And so forth, which is PLS and not just the polynomial.
Right. Yeah, that's correct. So S12, we got the polynomial time functions, and it gave a characterization of the strength of S12. For T12, we get projections of PLS functions, and we can view that as a kind of characterization of the strength of T12. Okay. Okay. So, okay. Good. Pause, unpause. So, everyone take a deep breath. Okay, now we can go on. Okay. So these are, I want to talk a little about, let's put that back up here. I want to just briefly mention second order theories. These will come back in towards the end of the lectures if I get to that stuff, but let me just pass it through you right now. We're going to use some of these techniques also in the meantime. Second order theories called U12 and V12, and they're formulated in a second order language. So what I mean by second order logic, so first order logic means quantifying over variables that, using variables that range over integers, non-negative integers. Here we're going to use, those are the first order variables. Second order variables are going to range over sets of integers. So we'll use capital letters like capital X, Y, Z, or Greek letters like alpha, beta, gamma. And some authors use one and some authors use the other, and I'm just going to confusingly mix both together on the slides. Okay, but they mean the same kind of thing. And from the computational point of view, rather than the proof theoretic point of view, you can view an X or an alpha as being an oracle. You're able to query the oracle about is some object T a member of the set X. We'll usually write that in first order logic as X of T. And essentially adding these things to the language is like adding an oracle symbol to the language. I talked earlier about adding a new polynomial time function symbol to the language and being conservative. Here we can also think about taking a new symbol capital X or a new symbol alpha and adding it to the language with no new axioms defining its properties, except we allow it to be used in induction formulas. So we redefine the notions of induction to allow oracle symbols, to allow second order variables to be used freely in induction axioms. Now quantification on second order objects is going to be a whole different ballpark, but just in terms of using them in the form X of T without quantifiers, we allow them to be used in induction axioms. And a side comment here is second order variables implicitly have polynomial bounds on their members because in our proofs, first order objects only range over bounded ranges of integers, and so whenever we ask X of T or write a formula X of T, there's always at least implicitly a bound on how big T is. So implicitly, we're only caring about finite ranges, only caring about finite sets. Okay. Okay, so that's second order logic in general. And then we can now think about, so let's just do this, okay, still not putting any second order quantifiers in. Let's just say first order logic augmented with second order variables. So we now, I sort of actually said this already a little bit here, sigma bi of alpha just means these formulas are defined just like the old formulas, sigma bi formulas, but now alpha of t counts as an atomic formula, quantifier-free formula, doesn't count towards the quantifier complexity. And then SI2 of alpha is then the same as SI2, except we're allowing induction on this enlarged class of sigma bi of alpha predicates. TI2 is the same thing. We're allowing induction on the enlarged class. And everything I said in the first lecture relativizes. So if you're familiar with relativization in the setting of theory of computer science, the same kind of thing works here. In particular, the sigma b1 of alpha definable functions of S1, 2 of alpha are precisely the functions that are polynomial time computable relative to an oracle for alpha. Same proofs all work, it just goes straight through. We didn't use anything special, particularly about the base functions. We just used the fact they were polynomial time computable. And so now we're treating the second order predicate as if it's polynomial time computable. In other words, we're allowing it to be used freely in the computation. And likewise, for T1, 2, the sigma b1 of alpha definable functions are precisely the projections of PLS alpha functions, which means PLS where the neighborhood and the feasible and the cost and the initial things may all depend on alpha. Okay. Okay.
So again, so alpha here is a set of numbers.
It's a set of numbers, yeah.
So when you see in the last theorem, alpha here is a fixed set of.
Well, what I'm thinking is I've got a, so this last theorem here, we're thinking of alpha as, well, it's a variable which stands for some set of integers, right? Okay. And we're now saying a function, polynomial time relative to alpha, you can think of an ordinary Turing machine computing it, and the only thing is that it's allowed to also make queries to alpha as an oracle. At any point it can stop and write out an integer on its query tape and ask, does alpha hold of this?
Right, so the theorem says for any fixed set of integer which defines language,
Yes.
the sigma b1 alpha for this fixed alpha definable function is p.
Right.
So
But I want to say, actually, you're saying the word fixed maybe in the wrong place in the sentence. I want to say that there's a fixed, so given that some sigma b1 of alpha thing is provable, where alpha is just a variable, there's a fixed Turing machine such that for any alpha, the Turing machine relative to that alpha finds the witness.
oh, I see. So alpha is a variable.
Alpha is a variable, yes.
Can you actually write down a formula in this language where you use alpha?
Sure. Let's say, for all x, there exists a y. If alpha of 0 and not alpha of x, then alpha of y and not alpha of y plus 1. Okay, so think of x as ranging over integers. And we're saying that alpha of 0 is true, alpha of x is false, implies there exists a y where alpha of y is true and alpha of y plus 1 is false. I can see if I can fit my not sign in there. Right. Okay. This is actually provable in S1 too, which may be a little surprising at first, because it looks like there's a potentially to just search from 0 up to x would be an exponentially long process, right? You know alpha 0 is true, you can look, check alpha 1, alpha 2, alpha 3 until eventually you find something that's false, right? But you can binary search. So a binary search algorithm can, ask, binary search. You ask alpha of x over 2, and then if it's true, you go right. If it's false, you go left. And then you ask alpha of x over 4, and so forth. And the binary search will let you find a y where you have alpha of y and not alpha of y plus 1. Okay, that's a binary search algorithm, which, as it runs, it asks queries of whether alpha is true or false of particular values, right? It doesn't matter. The algorithm works for any alpha and always succeeds for any alpha, right? And it's polynomial time.
In binary search, you should use the fact that y is less than x.
Oh, well, yeah, so I was, okay, well, it's true without the bound, but in fact we can prove it with the bound. Right, yes, good, yeah. Proving with the bound is even stronger, right? But of course that's all you have to prove that way, right? Okay, okay. Okay.
So, I mean, even though you're not using a quantifier, implicitly you're saying for any alpha this is true.
Yes, this would be, oh, so we can in general can put quantifiers on. We don't want to generally, but we can put that, we can say that if you can prove it without the for all alpha there, the rules of logic allow you to say for all alpha this is true, right? Okay. Okay. So we're also going to be dealing with this hierarchy of sigma b alpha of formulas over second order logic. So here we're going to allow quantifiers on these second order objects. You know, so we could say exists alpha or for all alpha, same as, you know, and then we can count alternations of second order quantifiers, ignoring bounded first order quantifiers, just the same way before we ignored sharply bounded quantifiers. Now we ignore bounded quantifiers, and we're completely disallowing unbounded quantifiers. They're just not permitted. But basically, the class, we're particularly interested in the class sigma 1b1. So these are the things of the form exists alpha 1, exists alpha 2, exists alpha L. We got multiple alphas, only existentially quantified. And then here I've got some formula A. And A is a bounded formula with no second order quantifiers. So this is what we mean by the class sigma b1. Sigma 1b1. Sorry. Okay. The 1 refers to the fact it's second order. I guess, sorry for that, but that's just the convention in computability theory. But we allow purely existential quantifiers, second order quantifiers in the front. Okay. So what computational class does this correspond to? The free variables here, we've got some free variables, you know, x, and first order objects x and second order objects alpha. What computational class does this correspond to? Hmm?
So your
Van? NP? It's worse than NP.
No, you're consulting an oracle.
You're consulting an oracle. Well, the point is you're asking, do there exist these second order objects here? Ben. Oh, shoot. Don't look at that. Okay, so he cheated. Non-deterministic exponential time, right? Because one way to verify this thing would be to guess the second order objects, right? And, well, and also guess a computation that verifies these second order objects satisfy this property. And then, okay. Well, okay. Well, I maybe only need that. So this is non-deterministic exponential time. So think of this as being an analog of NP, but up there in the exponential time. And the theorem then is, so now we do definitions look very much like before. We allow induction on these things, either P induction or induction. We call the theories U12 and V12. I'm only doing ones here. We need another axiom that says something that there's some second order objects exist at all, because it could be just the dumb theory where no second order objects exist. And we take comprehension axioms for this. If you studied set theory, you've seen these kind of axioms before. that take any, in our case, bounded formula with no second-order quantifiers, A. We're worried about the variable x in particular. We say that there is an alpha such that every x, alpha of x is true if and only if A of x holds. We allow y and betas as side variables. So this is just saying that there, for anything defined by a bounded formula, there's a second-order object that codes the truth of it. Okay, so this is the comprehension axiom. And we allow induction here, and then the sigma 1b1 definable functions. One is for u12, it's precisely the p-space functions, the polynomial space functions, and for v12, it's precisely the exponential time functions. Okay. And the general ideas of the proofs, of course, the technical details are different, but the general ideas are like the witnessing theorems we saw earlier. I think that's all I say about these things. Oh, well, there's something else, but that's all I say about these things. So, let me, well, okay. Let me give a summary of these things here. So this is a summary of the theory so far. We started off with S12 and T, well, we started with S12 and T12, and we were succeeded to get sigma b1 definable characterizations of the sigma b1 definable functions, firstly in terms of polynomial time, and secondly in terms of PLS. For U12 and V12, we have this much more complicated notion of definability, but we got p-space and exponential time. For SI2 and TI2, we weren't able to do sigma b1 definability. We've only done sigma bi definability. And we've gotten these classes p to the sigma bi minus 1 and PLS to the sigma bi minus 1. And of course, they have a conservativity result between these two, so you can state other results for them as well, right, based on the conservativity. So we've got a nice characterization of everything. We're particularly happy with the top two lines because these are the sigma b1 definable ones, the provably total. Okay, so that's where we are so far. Okay, this is a big pause because I have to switch to a different file of my PDF things. So good place, oh, questions before I switch to a different file. Only take a second to switch, it's on my computer.
So do you want to continue?
Oh, what time is it? Oh, 5 minutes? Oh, no, really? Okay, I guess not. It sounds like an early pause. So time for questions. Otherwise, it's lunch, right? No break, huh?
Lunch, yes.
Lunch, okay. Lunch is important. Okay, sorry, I lost track of time here, so why don't we go for lunch?
Yes, so,
When are we meeting?
We're back at what time?
we should be back on, let's see, at 3 o'clock, 3 p.m.
3, wait. Hold on, this is confusing. What's it in 24-hour time?
15?
Piet not set, Chasov? No? Okay, so 1500 or 3 p.m. for the North Americans. Okay, good. All right.
Okay, so thank you.